This table, you need to remember this table. You can either get a sample, we can say something about the population, we can either have an average or a fraction. Now we haven't talked about fractions at all yet. And like I said, when we are dealing with a fraction, we're not using standard deviations. So what on earth is my accuracy going to be when I'm talking about fractions? It's got a sigma in there, which we don't use for fractions, so we'll need some other formula to do this. So, it looks like this. Let's not look at this one for now, and focus on the other ones first. Now, this is the case we've looked at now, right? We had a mean from our sample. Sometimes you just have the data points from your sample. You have to calculate that mean yourself. Could happen. It's not that difficult. When you have your mean of the sample, you can determine the Z value by just choosing how confident you want to be, right? The Z value does not need any calculation. You just read it off from the table, and it's based on your own choice for how confident you want to be. Now I say your own choice, but that's absolutely bullcrap, of course. We choose how confident we want you to be on the exam. So you just have to follow that confidence level. But effectively, when you're doing your own market research, you can choose how confident you want to be, and that determines the Z value. Sigma is either given for the entire population, which was the case in our previous example, and the sample size you need to know. Now, when your standard deviation for the entire population is unknown, which will very often be the case, we will need to come up with some sort of plan to deal with that. And the way to do that is basically, we have a sample, we know the average from our sample, or either we can calculate the average from our sample. And if we can calculate the average from our sample, we can also calculate the standard deviation within our sample, right? So if you have the data points, you can calculate your average in the sample and the standard deviation in your sample. And the standard deviation was the sum of my data points minus my average divided by the sample size minus 1. You have to square root and square this, something like that. This is something you can then calculate. And now comes the problem when you do that, is that your distribution, your normal distribution, changes when you're using a standard deviation from a sample. Because normally, when we use the standard normal distribution, the standard normal distribution has a mu of 0 and a sigma of 1. When I do a sample and change this the other way around so that my mu comes at the boundaries and my sample comes at the middle, then the form of this normal distribution doesn't really change in this case, but it does when I replace my sigma with an S. So when I replace my population standard deviation, my sample standard deviation, the shape of my normal curve changes, which means it is based on a different distribution. It is no longer based on the Z distribution, but instead on something we call the T distribution, or sometimes referred to as the student T distribution. Now, this has no historical reason whatsoever other than the person who discovered this wanted to keep it a secret from other people in the world that were actually doing proper statistics. He wanted to make money off it, so he called it a student distribution, because then people thought it was just for students and no one did actual calculation with it. But it turns out this is a distribution that is used more often in the real world than the Z distribution. And it is basically found in the same table. Here we have the standard normal distribution, and the second paragraph is the student t distribution. Now it looks different. And the reason for this is that when we're dealing with a distribution, a t distribution, we are changing this to an s, which is now unknown, and the shape of this normal curve depends on your degrees of freedom, which doesn't really make any sense right now, but it is going to alter how broad or narrow the curve is going to be. Now this degree of freedom, we use it in physics a lot, where an elementary particle has multiple degrees of freedom. In this case, for now, and we'll talk about other degrees of freedom later on, but for the student t distribution, degree of freedom is very simple. We can calculate this this standard deviation from our sample, and in doing so we divide by a factor of n minus 1. The reason for this is fairly simple. If I have one data point, I cannot talk about any standard deviation from that data point, because one data point is always exactly on the average of the data points. But if I take two data points, now the average is somewhere in between, and each of these data points has a deviation from the mean. If I add a third data point, I get the same thing. All my data points now have a deviation from the mean, and that characterizes the standard deviation. But the standard deviation does not make sense for a singular point. There is no deviation from that point to the mean. So this is why we are dividing by n minus 1 when we calculate the standard deviation for a sample, and this is also why our degree of freedom becomes n minus 1. I have every new data point is free to be wherever he wants, but all but one data point actually gives me a difference on the mean itself, and thus we say we have n minus 1 degrees of freedom. Now if that doesn't make any sense to you, it doesn't matter. It's fine. Just remember the formula. Use it, determine the degrees of freedom, and let's say your degree of freedom, or let's say you do a sample of 20, then your degree of freedom is 19. You look in the table, you check 19, and then behind 19 there are 5 values. Each of the values corresponds to a specific right tail probability, so a specific area to the right. When using the t distribution, you can only choose areas corresponding to these numbers. In our case, we had an area of 2.5%, which would mean we look at this column, 19, so our number becomes 2.09. That is the value for t if you're doing it with a t distribution. We practice that during the workshop and practice when to use this. And before I move on with Before we move on from this topic and look at this horrible formula here, I would like to say that usually when you make an exercise, it will be on the exam or in the workshop, exercise book, whatever, usually it says we take a sample and the sample average is this with a standard deviation of this. In that case, when it is specified in the text that we took a sample which gave us a sample average of this with a standard distribution, with a standard deviation of this, it means that the standard deviation is of the sample itself. So you cannot use it as sigma, you have to use it as S. Often when it is given in the text after the sample mean, it means that it is the sample standard deviation. And thus you will have to use the t-test with a degree of freedom. Now this is one of the things that most often goes wrong on the exam. Knowing when to take the t-test or when to use the z-test, or the z-distribution or the t-distribution, right? That is one of the most important parts, and this is something we practice a lot with during the workshops. Now, should we just forget about this formula entirely and just focus on this one?
Yes.
Yeah, not this one. That's fine. Can tell you now that this one is not going to show up on your exam. That's how nice of a guy I am. This one is, however, often. No, almost every time. And it pertains to the fact that we sometimes have a sample fraction, known probability or a known fraction about the sample, and we want to determine the fraction for the entire population. An example, a company delivers products. They promise that when you order a product, it'll be delivered to you in 2 days' time. How often does this actually work out? Now let's say in 95% of the cases they are on time from the sample we took. Then how often for the entire deliveries of this company will they be on time? And it could be 95%, could be 94%, could be 96%. Depends on how big the sample is that we took. In that case, can't spell today, average, A becomes the formula we see there, which is Z times the square root of P times 1 minus P divided by N, which effectively means that sigma becomes that factor. So that's not really a possible conversion, but it works out in the formulas if you replace every sigma with the term P times 1 minus P. So that will be our accuracy when we're dealing with proportions, fractions, right? Now, one last topic we need to discuss, which is part of estimation. Well, first, when we're doing proportions, there are limits to the sample size that needs to be taken. So when we want to use this formula, you need to have asked at least 100 people or have taken a sample of at least 100. So for a company that delivers products within 2 days, I need to at least check 100 of those deliveries and see if they're on time or not to actually give us a good estimation. If I only take 25, I'm stuck with this thing, which isn't very difficult It's just a lot more work. But all of these factors are also in this formula. There's just a lot more of them. And it's a horrible thing to derive. So just make sure you ask more than 100 people and you'll be fine. You had a question?
Yes. You wrote that k is z times the square root, but on the sheets it's p plus or minus z times.
Yeah, so when we're dealing with a proportion, right, then instead of putting the sample average here, we put the sample proportion. And so this value is p, and the left and right bounds are found exactly a away. So if I want to give an estimate about the population proportion, it'll be between p minus a and p plus a. Or saying pi equals p plus minus a, or p plus minus this term. Yeah, that's the difference. So we'll see it again here, the accuracy between my sample average and my right bound or left bound is exactly the width of the accuracy. Now, from this, very often we want to do research, and if we want to do research, we need to determine first how many people we need to ask in order to give a proper, hypothesis about something. So let's say I want to give you the average length of the people in this room, and I want to be specific up to 0.5 centimeter, and I want to be 95% confident about that. Then my question is, how many people should I ask in this room how tall they are in order to be able to make such a claim? More than 100. It depends. Well, there's not 100 people in here, so it can be very specific if I ask everyone. But often the question is, how many products should I check in order to be confident about saying they're between these two values? And in that case, we are looking for the amount of samples I need to take, or the sample size I want to ask. And this is very important for your market research as well, right? Because you're going to want to do claims, make claims that you can give to the company itself. But in order to know how you can make that claim, you need to first know how many people you need to ask. And if you have a specific accuracy in mind and a specific confidence level in mind, then we can calculate how many people we need to ask to actually arrive at those numbers. And an example is given here. If I want to be 95% confident, then I know my Z value is 1.96. My accuracy, I claim I want an accuracy of 0.5 millimeter. In this case, I want A to be determined by myself instead of calculating it. From that, I can calculate the value of n. I need my population standard deviation for this, but I could also do this when I have the sample standard deviation, but then I need to use the t distribution instead of the z distribution. And we can also do this for proportions. Then I have to replace my standard deviation with the factor square root of p times 1 minus p. So the formula basically comes from this, and just squaring it and then rewriting it and get this expression. If I know these values, we can calculate an n. Obviously this sample needs to be a whole number. You can't sample 0.3 people. So we always round it up. We always round it up. Why do we always round it up?
Because if you have 138 people, 0.3, then if you ask 138 people, it won't be enough.
Won't be enough for what?
To be 0.5 millimeters, for example. So you always need to ask.
Was that also your answer?
Well, my answer was more like you can't have 0.3 people.
No, but
People
why
are
do we
always
round it
counted in
up?
whole numbers. Like if you take the case of a company,
Mhm.
a company cannot be 0.5 company. They're always
Absolutely.
measured in whole numbers.
Yeah, that's very true, but we always need to round up for the reason that the accuracy that we are trying to achieve, if we round up, the accuracy actually becomes a little bit smaller than 0.5 millimeters. If we would round down, the accuracy would be a little bit over 0.5 millimeters. Getting an exact accuracy of 0.5 millimeters would require an exact sample of 138.3. Increasing sample size makes a better accuracy, so shrinks your accuracy interval. Decreasing sample size increases your accuracy. Now, the last bit I want to go over is when your standard deviation is unknown, you use the sample standard deviation, which you can determine yourself if you've done a sample. Now here comes the problem. When I want to know how big my sample size should be, I can't use a standard deviation from that sample because I haven't done the sample yet. I'm still trying to determine how big the sample needs to be. So this often happens where you have no idea what the sample or what the population standard deviation is, so you want to use the sample standard deviation, but right now we're still determining how big our sample needs to be. Now, the only solution you have, which is absolutely not a feasible answer, is to do a pre-research or survey. So first, I just ask 10 people. From that, I get some standard deviation from my sample. I use that to calculate how many people I should have asked, and I get a new number which is probably a lot bigger than 10. This number is not correct. It can't be correct because it's based on a different sample with a different standard deviation. So you'll always make some error. The only real solution you have is do the pre-research, do the little survey beforehand, determine a number n, and then ask more than those people. Because else you'll have errors and your accuracy will be bigger than you want it to be, or the accuracy number will be larger than you want it to be. Now, lastly, for proportion, we can do the same trick. We can separate n from this equation, rewrite it, and we get this formula. Now, when you are determining what sample size you need to use in order to determine some proportion, in that case your proportion is obviously from the sample is unknown because you're still determining how large a sample should be. Now in that case, if P is unknown, we can use an estimation of the entire population proportion. Sometimes, very, very rarely, you might already know what your population proportion is roughly going to be. Like, for example, I know that 90% of most deliveries in the Netherlands will be on time. So I can use that as an estimation when I do this sample, when I'm trying to determine what sample I need to take. But if you don't know, you need to use 50%. as your estimate. And the reason for this is very simple. I can graph this function. Just, you know, business mathematics, graph a function, just plug in some numbers, 0, 1, if I plug in 0 I get 0, if I plug in 1 I also get 0, if I plug in a half I get 0.25, and if I plug in, let's say 0.3, I get 0.3 times 0.7 is 0.21, which is somewhere here, and the same goes for 0.7, so it looks like this, roughly. Should be symmetrical, but I can't draw, so. Anyway, 50% is the maximum. You can also do it by, you know, finding the derivative, equaling it to 0, finding extreme value. You see that's the maximum at 0.5. However way you do it, when you're going to try and find out how large your sample size needs to be, if you have no idea about your sample proportion or your population proportion, it is best to take 50% because this maximizes the term above your fraction, which means it also maximizes this number n, which means you're always overestimating how many people you're asking instead of underestimating. And that is why we use 50% in that case. Now, I've talked enough, I think. There's some thing that I need to discuss during the workshop, I think. We don't have time anymore. But it has to do with the fact that if I am asking a certain group of people about, for example, their length, how tall they are, and I'm asking a significant proportion of the entire population, it will actually have an effect on my accuracy. If I have asked a very large amount of people from the entire population, there is less room to deviate from the average I found in the rest of the population. I'm going to give an example during the workshop about this, which is going to make it more clear, but it's called the finite population factor, and we're going to add this to our calculations when we know the entire population. Right? I think tomorrow